All right, welcome. Today, we're going to jump right into the single most important step you take before writing any computer program. You've got to have a plan. And in the world of code, that plan has a special name, the algorithm.
I mean, let's be honest, who hasn't? You know those tedious tasks? Calculating expenses, sorting through endless files, all that stuff you wish you could just hand off. Well, that is exactly what computers are for. But how do we actually get them to do what we want?
Well, it's definitely not magic. Before a computer can do anything for us, we have to give it a perfect step-by-step set of instructions. Think of it this way. The computer is just the worker. The real intelligence, the strategy, that comes from us. It all has to start with a human plan.
Okay, so let's dive into that plan. In programming, this blueprint, this recipe that has to exist before you even think about writing a single line of code, is what we call an algorithm.
So what is it, really? An algorithm is just a list of well-defined instructions. It's kind of like a recipe for a cake. You have your ingredients, and you have a very specific list of steps in a very specific order. You follow them perfectly, and boom, you get a cake every single time. Miss a step and, well, you don't.
And you know, this isn't some brand new tech buzzword. The idea has some seriously deep roots. It's actually named after the Persian mathematician Al-Khwarizmi, whose work laid the groundwork for algebra and systematic problem solving. We're talking nearly 1,200 years ago.
Now here's the real magic of using an algorithm. It lets you separate the problem solving, that's the what you need to do, from the actual coding, which is the how you're going to do it. It means you get to focus purely on the logic, on solving the puzzle first, without getting all tangled up in the strict rules of a programming language.
So, how do you actually build one? It's a pretty structured process. First off, you have to really understand the problem you're trying to solve. Then, you break that big problem down into smaller, bite-sized pieces. For each little piece, you figure out what info you need to start with and what you expect to get at the end. And only then, once all that is crystal clear, do you actually write out the step-by-step algorithm.
Right. So, every great recipe needs ingredients. Let's take a look at the basic building blocks, the ingredients that you're going to use to put your logical plan together.
So your algorithm is going to handle information using two kinds of containers. A variable is like a labeled box where you can swap the contents anytime you want. Think of the score in a video game that's constantly changing. A constant, on the other hand, is like a box where the value is written on it in permanent marker. It's set once and it never, ever changes, like the value of pi.
Okay, so we've got these containers, our variables and our constants. But what kind of stuff can we actually put inside them? We can't just throw anything in there. We have to be really specific about the type of data we're working with.
And here are the usual suspects. You've got integers, which are just your basic whole numbers, like 10 or -5. Reals are for numbers with decimals, like 9.81. Then you have Booleans, which are super simple. They can only be true or false. A character is just a single letter or symbol, like the letter A. And a string is just a sequence of those characters, like a word or a whole sentence.
So, we have our data containers, and we know what kind of data they can hold. But how do we actually make them do things? We need some rules, some action words to make our instructions smart and get things done.
And these action words are called operators. They are the symbols that perform operations on our variables and constants. This is how we do the actual work, whether it's adding numbers together, comparing two values, or making a logical decision.
Now, a lot of these you'll recognize right away from math class. We have our standard arithmetic operators for doing math, and then we have what are called relational operators, which are all about comparison. Is one value less than, greater than, or equal to another? The answer to that question is always a Boolean. It's either true or it's false.
Okay, and this is where your algorithm really starts to get smart. How do we combine those true or false conditions? That's where logical operators come in. And means both conditions have to be true, or means at least one of them has to be true, and not just flips the value, turning a true into a false and a false into a true. This is really the foundation of all decision-making in a program.
Okay, we've got our ingredients, the variables and data types. We've got our rules of logic, the operators. Now let's see how we put it all together to build that formal blueprint, the one that's ready to be turned into a real program.
A proper algorithm has a really clean and clear structure. First, you give it a name. Then, you define any constants you might need. After that, you declare all the variables you're going to use. And then, everything that actually happens, all your instructions, goes right there between begin and end. It keeps everything super organized. And inside that structure, you're mostly doing three main things.
You're reading input from a user, which you might see written as lire, which is just French for read. You're writing output to the screen, shown here as a creer, or write. And finally, you're doing assignment, which is just the simple act of putting a value into a variable, represented by that little arrow symbol.
So at the end of the day, what makes a great algorithm? Well, it has to be exact. It has to give the right answer every single time. It has to be clear enough for another human to understand it. And this is critical. It has to be efficient. The difference between a good algorithm and a great one, for say searching data, can be the difference between getting an answer in a millisecond or in 3 hours. You have to remember, a fantastic program can only be built on the foundation of a fantastic plan.
And that's really the heart of it. An algorithm is pure problem solving. It's the thoughtful, creative, human part of programming. So that leaves us with one last question for you to think about. Now that you have this way of structuring a solution, what's the first tedious task in your life that you would choose to automate?